Hello everyone, so we're going to start this as a real class, and we're going to do a do now. So you can pause the video now and do the do now. We're going to go over it the first thing when we get to class on Thursday. We're going to go over this right away. Please do it on your do now sheet. We're going to go over this do now as soon as we get into class on Thursday to save time, because on Thursday we're doing a lab. I want to make sure that this gets done so you can use the most time for the lab. So pause the video, do the do now on your do now sheet. It counts as a do now. And then we'll go into today's lesson. Okay, I hope you guys did the do now. If you didn't, I'm going to be very unhappy. So make sure you did the do now, and so that we can go over it in class on Thursday. Today we're going to talk about vapor pressure and how you can collect gas over water to determine the number of moles of gas you've created in a reaction. So before we get into the problems, we're going to do some conceptual stuff. So the first question is, what is vapor pressure? And vapor pressure is the pressure that's exerted as a liquid turns into the gas on the walls of a container. So here we have liquid A, and here we have liquid B. Liquid B would have a higher vapor pressure because there's more molecules of vapor. And since there's more molecules of vapor, they're going to hit the wall more, so there'd be more vapor pressure created in this container by liquid B than in this container, which has less vapor or less particles in the gas phase. So it would have a weaker vapor pressure or a lower vapor pressure. So there's something called equilibrium vapor pressure. And if there's enough of the liquid, it doesn't have to be water, but if there's enough of the liquid in a flask, and the flask is capped so the gas can't escape, you will result in an equilibrium vapor pressure where the particles keep on going in and out of the gas and liquid phase, and they'll reach an equilibrium, and that pressure in the closed flask will stay constant. Now, the AP exam loves conceptual questions like this, especially on the multiple choice. They want to discuss factors that affect the equilibrium vapor pressure. And there are only two factors that affect equilibrium vapor pressure. The temperature of the liquid and the intermolecular forces of the liquid. Nothing else, not the surface area or the volume of the liquid or the amount of the volume in there affect the equilibrium vapor pressure. Just the temperature of the liquid and the intermolecular forces of the liquid, or what it is and the strength of its intermolecular forces. And we're going to discuss how these two factors affect equilibrium vapor pressure. Do they make it higher or do they make it lower? So here we have two flasks. One is in room temp, and one is on a hot plate, and the liquid is being heated up. And the question is, which one will achieve a higher equilibrium vapor pressure? And the answer here, as you'll see, you probably can guess, or you can guess in your brain, the answer here is flask B. Okay, so why is that? The reason why that is, if you're heating the liquid, more molecules are going to be able to escape the liquid and turn into the gas phase. So you'll have more gas particles because it's hotter and more of the liquid is evaporating. So you'll have more gas particles in the gas form, which will hit the side of the flask and create pressure. Where in the colder flask, or the room temperature flask in this case, less of the molecules will be able to escape and turn into a gas. So you'll have less gas particles in the flask, and therefore less gas particles hitting the sides of the flask. This is a graph of the temperature of water in this case, and the vapor pressure. And as you can see, while vapor pressure does increase with temperature, the relationship is not linear. At some point, it starts increasing almost exponentially. And here you can see, as my cat is making scratching noises, that here you can see that when you reach 100 degrees Celsius, that's the boiling point of water, the vapor pressure increases almost exponentially, or much faster than it did before the boiling point of water. Because at this point, many of the particles are turning into gases at the boiling point of water. So the at that point, the vapor pressure increases much faster than before the boiling point of water. But it's just important to know that the relationship is not linear, and it starts increasing faster when you get to the boiling point of the liquid. So here we have the same graph. The black line is water. And we're asking which curve would you think would represent the vapor pressure of the curve for, let's say, ethyl alcohol? And the answer here, so the answer is either the blue line, the black line, or the red line. And if you know anything about alcohol, alcohol has a lower boiling point or vaporizes easier than water. In fact, I'm using alcohol hand sanitizer. You know, you wipe it on your hands and it vaporizes pretty quickly. So alcohol is going to create more vapor pressure at a lower temperature. So the blue line here represents alcohol as it starts going steeper earlier. It has an earlier boiling point, so it starts turning into vapor faster than water does, because it has a lower boiling point, much lower boiling point than water. So we also said that intermolecular forces, and let me get my little pen tool out. So intermolecular forces also affect vapor pressure, and liquids with weak intermolecular forces have higher pressure, have higher equilibrium vapor pressure. And you think about that, makes sense, because if we have a glass, right, and there's a liquid in here, if the molecules are attracted to each other, they're going to have a hard time vaporizing. They're going to stick together and get pulled back down. Whereas if you have another liquid, right, that has a weak intermolecular forces, the molecules can escape, and they're not attracted by the liquid, so there'll be more of them, and they'll create a greater vapor pressure because the molecules won't be pulled back into the liquid by their intermolecular forces. More of the gas particles, more of the particles will be able to escape and be far apart from each other in the gas phase. And since you'll have more gas particles and less particles being pulled back into the liquid, they'll hit the container more, and then you'll have a higher vapor pressure. Okay, so this ends the sort of conceptual part. Sorry if I got cut off here. This ends the conceptual part of today's lesson. I'm going to upload this video, and then we're going to do the math part. And the math part is about 4 slides. But I'm going to upload this conceptual part just so I'm not rushed with the math. And then we're going to do the math part in the next video.